Fang Yi from National University of Singapore. She's going to present a recent working paper relating to coal mine and also environmental issue. And so we'll have a presentation, 60 minutes, and followed by Q&A question. Please feel free also if you have any other clarification question you'd like to ask her. Please feel free to unmute yourself and ask a question directly, or you can also put your question in the chat. So I will read up your question if any. Right, Fang Yi, all to you.
Okay, thank you, Tianfu. Let me share my screen. Does that work?
Yeah, that's right.
Okay, great. Okay, so good morning, good evening, everyone. Thanks a lot for giving me this opportunity to present our working paper on unintended consequences of coal-fired power plants closures evidence from China. I'm Yifan. I'm an assistant professor from the Department of Real Estate at the National University of Singapore. So this paper is co-authored with my PhD student, Qiuxia Gao, and also Chen Tan, who is an assistant professor from the Nanyang Technological University. So let's first look at this picture. So where is this one? This is a view of the Shougan's Qian'an still working in Tangshan City in China in 2016. So this is one of the many cities in China during that time period. You can see there are a lot of pollution generated from the coal-fired power plants. And actually, the coal combustion from heavy manufacturing industries and power plants is a major source of air pollution in China during that time period, which contributes to around 80% of SO2 and about 35 to 40% of PM of the national's total emission. So how to address this kind of heavy pollution issue and how to meet the carbon neutrality and global 1.5 degree Paris Agreement goal? The Chinese government tried hard to reduce the pollution, such as they enforce a stringent emission standard, they increase the pollution discharge fees, or they conducting more series of inspections, or increase the alternative to the coal-fired power plants, such as renewable energy and natural gas for electricity production. But one of the most straightforward way is that let's just retire the old and pollution inefficient coal-fired plants. So we want to know what's happening for this kind of massive retirement of coal-fired power plants and what's the outcome on the environment. Okay, so let's have a simple illustration of what's happening. So what we can see here is that there are a lot of different kind of coal-power power plants in China. They vary across the size, the operating years, the production efficiency, and the emission intensity. So we know that those kind of larger and newer ones, they produce marginally less of the pollution because they can produce more of the electricity. So the problem is that once we close one or two of them, such as the green dots shown here, how can we meet the total electricity demand? So as we calculated here, say that before the closures, the total electricity demand is, say, 5,000 megawatts. When we close two of them, the 750 megawatts are shut down. So how can we compensate for those 750 megawatts? Given that this kind of electricity demand, consumption demand does not change. So let's think of several ways, these are the ideal intended scenarios. If we close two of them, scenario one is that we can allocate them to the renewable power plants with close to zero marginal cost, such as shown here, using the solar power or the hydropower, can be within or outside the administrative boundary, say the province level. So the relatively ideal scenario B is that, okay, let's do coal-fired power plants to other provinces or other places, but in a relatively remote regions with less exposure to the local communities. This is relatively ideal scenario B. And another consideration is that, hey, we can allocate to some safe nuclear power plants. So these are those three relatively ideal scenarios. But what is not so ideal is that when we close those green dots, the power plants, we just add on to the operating power plants in the nearby neighborhood, such as to those nearby ones and to those nearby ones. They just intensify the electricity consumption or production for those neighboring power plants. So what will happen in China? What is truly going on in China? So if we think about all these kind of alternative ideal or not so ideal cases, we find that there are more questions actually than answers. So what kind of questions we can ask in this context is that, first, do we observe a transition of energy production from the coal to other cleaner sources over this time period, such as what we show for the scenario A and scenario C? The second question we want to ask is that, do we observe a reduction in the electricity consumption? So from the demand side, do we see there is an ongoing trend for electricity consumption across the years, or it's just a stable or even going down? The third question we want to ask naturally is that, which power plants do the planners choose to close? Do they really close those dirtier ones with the higher marginal social cost? And the last question we want to ask is that, hey, are there any impediments in this kind of procedures for those planners to close? And are there anything happening to reduce their incentive to dispatch electricity quota to the plants with the lowest marginal social cost? So with all these questions, we want to first look at some stylized facts. What's truly happening in China between 2000 and 2014. So this graph will show that the number of coal-fired power plants closures during that time period. So we can see that, as shown by the green bars, there are increasingly more coal-fired power plants closed during that time period. Actually, more than 180 power plants were closed during the 14 years, and which induced a reduction in the operating capacity of about 70 million megawatts. Okay, so this is about the first. So across the geography, we can see that before 2000, there were just several of the closure of the coal-fired power plants, which is similar during the 2001 to 2005 time period. But from the 2005 and onward, we can see there is a massive closures of the coal-fired power plants, and which also going on to the 2011 to 2014 time period. And of course, those kind of closures of coal-fired power plants is not random. And in about 2 slides, I will show that which kind of coal-fired power plants are chosen to be closed. And the second question, if we recall our second question, is that, do we observe a reduction in the electricity consumption during that time period? So in short, the answer is no. As we show by this green line, across the years, there is an increase in the consumption per capita for the electricity. And although we see that along the years, there is a relatively decline in the share of coal-fired electricity, and there is an increase in the electricity generated by the renewable. But overall, the consumption demand for electricity is increasing drastically. And the third set of stylized facts we want to show is that what kind of power plants other planners close in China. So we separate those kind of coal-fired power plants into 4 categories. One is completely closed ones. The second is partially closed power plants, but without the new units opening, which means that they are in the way to be completely shut down. And the third one is partially closed power plants, but with a new generated units working or opening. And the fourth one is about the fully operating one. So there is no closure or shutdown for any of the units. So we look at the average capacities, we find that it's relatively smaller of the coal-fired power plants that are closed. And if we look at the age, they're relatively older with longer operating hours, as we show here. And also, they have relatively higher level of SO2. In other words, they are more polluted. And they are located in more population-dense place, such as we can show here. For those completely closed ones, they have higher population density, and in the more industrial-oriented region. So in short, it seems that the planners are making the right decision. They choose those smaller power plants and older and in the more polluted areas with more densely populated regions to shut down those power plants. And the last set of questions with some style facts and institutional background is that whether we have some impediment to dispatch the quota to efficient power plants. So think about this question is that when we retire those kind of power plants as shown in this graph here, the natural question is that how can we dispatch? How can we dispatch the quota, whether to other efficient power plants or not? So what's happening in China is that different from the other part of the world, which is more like a merit-based system. China, for a long time, we have this equal share system, which means that the dispatch is based on the equal share. Generators allocated almost a similar number of operating hours disregarding the plant efficiency. So the rationale behind is that to prevent the power shortage in some regions, because historically there is always an electricity shortage across China. And the second one is to ensure the fairness among the power plants operators. And given that the operating hours are evenly among the coal-fired generators despite of their age, size, efficiency. So does that mean that the quota from retired power plants are distributed evenly or say inefficiently? So fortunately, we have the reform in 2007, which introduced a differentiated generation quota scheme in 5 provinces. So they take the pioneer to be more like the merit-based. They adjust the dispatch quota based on the technical specifications, which means that the larger, more efficient power plant and less polluting generator units will be allocated of the more utilization hours. So this is what's happening in the China's we're transferring from the equal share system to more like the merit-based system. But the second thing is that do we consider any impediments across administrative boundary? So the answer is yes. There is some limits in the cross-province trading. There is a lack of coordinating between areas to trade electricity production quota. So also in 2007, we have this kind of generation rights trading, which allow decommissioned units to transfer quotas to operating units, but it's restricted in some of the region in China. It's not nationwide. And also we have the prerequisite, which means that the quotas must be allocated from less efficient and more polluting plants to more efficient ones with lower emission. And in this process, the province still serve as a primary dispatch zone, with a between-province dispatch of electricity is quite limited before the market-oriented reform in the power market in 2015. And unless they face a true shortage of electricity, the province do not import electricity from other provinces. And also, so for the provincial leaders, they're reluctant. They do not have that much of incentive to reduce utilization hours of their generators because they still want to keep profitable, as a compensation scheme is depend on how many of the electricity to generate. Okay, so we can see in this graph is that along the years, although there is increase in the market-based transaction as marked by those light blue and yellow bars, but most of them is intra-province as shown by these light blue ones. But for the inter-province market-based transaction, they are quite limited as shown in this yellow part. So we see that still there is some administrative boundary or say impediments in those kind of cross-province trading.
Fine. Just quick clarification. Who actually own those power plants? Either local governments or private sector? Or
okay, so most of them they are like the local government, they are the administrative ones who are taking care of this, like national or state-owned ones. So the provincial leaders, they can make the decision on much of the saying in this process. Okay,
thanks.
so yeah, thank you, Tianfu. So the third side is that we consider this kind of big picture is that we are in this kind of transitional process to switch from the coal to the renewable energy. But as we have any incentive, or do we lack any incentive to do such kind of smooth switching? So yes, sadly, there is such kind of lacking of incentive. Because when we think of this electricity price is high, the price of coal are relatively cheaper. So it's still profitable to carry on to operating those coal-fired power plants. And think on the other side about renewable energy. Although they are cleaner, but now they are uncertain, they are unstable. And also the coal-fired generators, they are generally not compensated for providing service to support the renewables. And because of the feed-in tariff on the renewable energy, which are higher than the coal power, it's also expensive to import the renewable energy to replace the coal power. And when we think about this kind of investment on relatively more efficient coal-fired generations, there seems still to be continuous investment to replace the old plants with newer and more efficient coal-fired power plants. Why? Because the local leaders, they have the incentive to encourage such kind of construction because it contributes to the local economic growth. So with all this set of institutional impediments, we want to know what's truly happening in China and how can we contribute to reduce such kind of impediments and to increase the air quality. So let's summarize what's the research question in our paper. So first is that we want to document the classical closure effect. Does closing the coal-fired power plants improve the local air quality and how much they improve the local air quality? The second is that we want to take one step further. We want to know that do we observe the air quality worsening around the neighboring coal-fired power plants that remain open? Do they truly redistribute the pollution from the closed power plants to other operating ones? And if so, what are the determinants of such displacement in the context of distortion and how we can reduce such kind of distortion and displacement? And the third is that if we're taking the closure effect and displacement effect together into consideration, what is the net exposure? Say that what's the overall improve in the air quality and how we can improve the net exposure effect. All right, so in a simple graph, what we want to know is that when we close these green dots, what's happening in the neighboring operating power plants? Okay, so how can we link with the literature? So in the literature, they look at the closure effect, and generally the literature finds that there is an increase in the air quality in the local vicinity, which is not surprising. And in the China's context, the 2018 PNAS paper, they find that there is a decrease in the SO2 about 14%, but they just look at the large-scale one-time cut of the July 2014 deadline for implementing tighter emission standards in China. So what's different from them is that we look at this kind of staggered closure for a longer time period and what's the impact on the SO2. And also, some of the literature they look at the impact on the health, such as a reduced mortality rate, and also this kind of improved health status of the children. So different from all this set of paper, we want to look at the general equilibrium, which means that we not only look at the local vicinity of the closed power plants, we also look at what's happening in other operating power plants. So this is how we link with the literature on the effect of closure on environment and health. There is also another set, several of the leading papers, they look at the displacement effect. So usually they focus on those kind of shutdown of nuclear power plants. They look at what's the displacement effect to the coal-fired power plants or to the other of the natural gas power plants with the closure of the nuclear power plants. And there is another paper which also look at the change in the greenhouse gas. But in our paper, what is different is that we want to look at the environmental benefits of plants' retirements to make it more clearer. And also, we want to put it in the context of the transition to cleaner energy, and also with such kind of institutional distortion, we want to know that if there are dispatch inefficiency, and if there is inefficiency, how we can overcome and how we can improve the overall efficiency. Okay, so this is how we contribute to the second set of literature. So this is an overview of our strategy and results. So we did a lot of data work. We manually collect information on more than 1,700 of coal-fired power plants in China. We also manually collect more than 8,000 of renewable energy plants across China. And then we combine with the NASA satellite data on the SO2. And we use a staggered coal-fired power plant closures in China as a quasi-natural experiment from 2004 to 2014, and we use the DID estimate. Okay, so what we find is that we identify those 35 km around the retired power plants as a treated group and 35 to 50 km as a control group. And we find that there is an decrease in the SO2 in the vicinity of the closed power plants by almost 2.4%, which indicating an increase in the air quality. But at the same time, we also find significant evidence for the displacement effect, which means that with the close of power plants A, for the power plants B, which is operating and in the neighborhood of closed power plant A, the air quality around the power plant B is getting worse. So by about 1.7%. So if we take these two strengths into consideration, and if we take the population density into account as well, our final result shows that the net exposure effect is only about 4.3% of the closure effect, which means that there may be some overestimating for the impact of closed power plants in China. Okay, so what's our contribution of this paper? So use a lot of data work. We try to improve the understanding on the overall environmental outcomes for the plant closures. Not only look at the partial equilibrium, but also at the more general equilibrium. And different from the one cut of the policy shock, we look at an inference for a massive wave of plant closures across 2004 to 2014 for 1 decade. And also we both document both a closure effect, displacement effect, and the net effect. And methodologically, we try to contribute because a lot of previous data, they use a monitoring stations data, which we need to take a lot of other factors into consideration, such as the distance between this monitoring station and the observed air quality place. But in this paper, we use a more granular level data. We use the NASA satellite measures, try to provide a more accurate estimate on the SO2 levels at a more granular level. And the third is that we truly want to draw more policy implication, because when we think about this kind of dispatch inefficiency, when we think about all the impediments for the allocation, we really want to know how can we mitigate the displacement effect? What are the specific ways to overcome such kind of institutional obstacles? Okay, so let me briefly introduce about the data set. We combine for 3 sets of data. The first is about the power plants. We manually collect the information on the location, on the starting year, retired year, and the capacity of coal-fired power plants from the Global Energy Monitor website, which is a publicly available website. So we identify 152 retired power plants and calculate the number of retired generator units and retired capacities as well. So we also match those kind of retired power plants with SO2 levels as a grade level. And for the environment, what's the data for the SO2? As I mentioned before, we use the NASA information, and at a more granular level, such as the 0.25 degree times 0.25 degree of the grid, and we aggregate as a monthly level, and we replace the negative values in this data set with 0, follow the PNAS paper. But in one of the robustness check, we also replace the negative values with, we just deal with it as missing, and the result keep robust. So our final sample include about 727,000 observations for closure effect, I mean, in the neighborhood of closed power plants, and 2.5 million observations for the displacement effect, which means that in the neighborhood around those kind of operating power plants after the closure of another power plant. All right. And we control for a bunch of climate controls, such as the temperature, such as the air pressure relatively to mean sea level, the visibility, the wind speed, and others. We use the inverse distance weighting, and we combine them all together for those 3 sets of data. And our identification strategy is quite straightforward. So the first line shows about the closure effect, which means that we have the dummy variable of close equal to 1, where the grade I is within 35 km of the retired power plants. And 1 is equals to 0, which means that it is in the control group between 35 to 50 or between 35 to 100 km. We have different specification of the control group. And the post is also a dummy variable equal to 1 if the year T is after the power plants retired, and 0 otherwise. And we control for a bunch of climate controls, as we mentioned before, and also their second polynomial. We also control for the year-month fixed effect and the grade fixed effect and other fixed effect, which we will show granularly in our later empirical specification. And the second line will show our identification strategy for the displacement effect. Everything is the same as the closure effect, except for this measure of near. So what is near? Near means that one of the operating plants, which is within 100 km of the closed power plants. But near means that within 35 km of the operating plants. Okay, so this is what's our definition of near. So let me make it clearer as show about this graph. So in this graph, this part is about the closure effect. Within 35 km of the closed power plants, we define as treatment. And for instance, 35 to 50 km, we should say that that's a control group. So this is about the closure effect. And when there is a power plant closed here, we look at the other operating power plants, which is within 100 km of the retired power plants. We define within the 35 km of these operating plants as a treatment for the displacement effect, and between 35 km and 50 km as a control group under the treatment, under the displacement effect. Okay, so we use this graph to show about our identification to visualize our empirical strategy. All right. So this,
when you have more than one this power plant in the displacement area, how do you deal with those things?
Yes, so we have one of the robustness check. So in the main identification, we have different, say that the different opening plants included. But later we have one robustness check, which will reduce this kind of overlapping of the power plants. Then we show the robustness of the result. But your concern is very valid. We think that this is one of the stuff we truly need to check about.
Okay, thanks.
Yeah, so thank you. Okay, so this is about the summary stats at the grade level. So I want to show you about two graphic evidence, which is quite straightforward. So in this one, it shows about the closure effect. So the closure effect, what we are doing is that we regress the log SO2 on a bunch of the control variables and with the plant year month fixed effect and province by year fixed effect. And we plot the residuals on the y-axis and on the axis, which is a distance to the closed power plant. So the blue solid line shows about the SO2 level before the closure, and the red dashed line shows about the SO2 after the closure. So clearly we can show that there is a reduce in the SO2 level after the closure of the power plant in the vicinity of the closed power plant. It's quite straightforward for this one. And another striking graphic evidence is that we visually observe this displacement effect. So what's happening here is that what's the SO2 level around the operating plants within 100 km of the closed power plant. We can see that before the retired power plants, is about stable here as shown about with the blue solid line. But after the closure of the power plants, what's happening in those operating plants is that we observe this kind of sudden increase in the SO2 level around the opening or say operating power plants. So this one visualizes our findings on the displacement effect. So someone will ask, why you choose the 35 km as a cutoff for the treated versus control? So our answers are from the two aspects. One is that we adopt this cutoff of 35 km from the literature. Several papers, they also adopt the 35 km for the definition of treatment group. And the other is that it also fits our context, because if we choose this kind of distance band, 0 to 5, 5 to 10, 10 to 15, and we run such kind of regression, we can see virtually that after 35 km, it's not that significant for its impact. So by this kind of identification justification, we are confident that we use 35 km as a cutoff for the treatment versus control group. And this table shows about our baseline results. In panel A, we show about the closure effect, and in panel B, we show about the displacement effect. So in column 1 to 4, we include the year-month fixed effect with different level of such as the province fixed effect, city fixed effect, county fixed effect, and the plant fixed effect. For instance, for the closure effect, we observe a stable decrease and significant at a 5% or 1% level around this kind of closure power plants. Okay, so the magnitude is quite stable from 2.3% to about 3.1%. But in 1 to 4 column, we define the control group as beyond 35 km and less than 100 km. So someone will argue that your control group is too large. It may have some confounding factors there. So in column 5 to 7, we refine the control group to be within 50 km, which is between 35 km and 50 km. So we also show here that this kind of closure effect is significant. And even if we control at a more granular grade level and including the province time year fixed effect, we still see this kind of robust and significant decrease in the SO2 level. We use the last one as our preferred estimates of 2.4%. And this is about the closure effect. And in panel B, we show about the displacement effect, which means that we look at what's happening around the opening plants. Okay, so we show that consistently there is an increase in the air pollution around the operating plants, with a varying in the level of magnitude, but relatively stable. So we choose the last estimate as our preferred estimate because it controls for the year, time, month fixed effect as a granular grid level, and also we control for the time varying province and year fixed effect. So we also carry a bunch of robustness tests because, as Tianfu just mentioned, if there are overlapping of the treatment and what happening to others. So let me go through for the details of the robustness test. So in this one, we consider about 9 alternative stories. So the first is that in the baseline estimate, we remove the negative SO2 with 0. So what if we just leave it as missing? So we replace them as a missing variable, and we find that we still have robust evidence on the closure effect and displacement effect. And the second concern is that whether we have some outliers for the SO2 level. So we remove the top 1% and the bottom 1%, we still say the estimate and level of significance remain robust. And if instead of clustering as a plant level, we cluster as a county level or cluster as a grid level, we still find the similar level of statistic significance. And the column 6, what we are doing is that we use the retired power plants without new built units after closure. Because if after the retirement they have some new built units, they may complicate our story. So in that way, we look at a smaller subsample, and for those once we shut down, they truly shut down. There is no other opening, and we find that the result keep robust. And in column 7, this is what Tianfu mentioned, is that, hey, there may be the different operating plants around one of the closure power plants. We consider this one, and we remove the overlapping treatment, we still find the significant result. And in column 8, because in recent years, there is a lot of paper talk about this heterogeneous treatment effect. So we conduct the CSDID estimate. We consider this kind of heterogeneous treatment into consideration, and we still find there is a significant reduction in the SO2 around the closed power plants, but there is an increase in the air pollution around the operating plants. So the last column 9 was column 9 here shows is that in the baseline estimate, we aggregate the SO2 level as a grid level. But in the PNAS paper, for instance, they aggregate by distance band, which means that aggregate by the treatment group and the control group. So we follow this one, and we have a much smaller sample, but still we have robust result on the closure effect and displacement effect. And in the last column, we test on the distance. So remember how we define those operating plants is that they need to be within 100 km with a closed power plants. So here we think that, hey, what if for those power plants, they are operating, but they are beyond 100 km, specifically within 100 km and 200 km, do they have any, say, spillover effect? So the result is not significant, which justify what we're doing is that we specify those kind of operating plants to be within 100 km. So they're not that further away. The air pollution still can go to that specific place or say spill over to that specific operating power plants. Okay, so that's about our robustness test. And of course, we show this kind of pre-trend. What's happening here is that we use a blue dot to indicate the displacement effect and the red square to indicate the closure effect. So our estimate shows that before the power plant closures, we see relatively they hover around 0 for the estimated effect. But right after this closure of power plants, we see that the air quality, the SO2 level around the closed power plants experience a decrease along the years. But for those power plants which is operating but in the neighborhood for the closed power plants, we can say there is an increase in the level of SO2 around the operating power plants. So this kind of graph still holds if we use a CSDID setting, take the heterogeneous treatment effect into consideration. So this is about the graph we replicate by use the CSDID, which also shows a similar pre-trend and post-trend. All right. So if we take the closure effect and the displacement effect into consideration, we are curious to know what is the net exposure, because the displacement effect offset the closure effect in the neighborhood. Okay, so what we're doing is that we extract the beta and the delta from the last column from our baseline estimate about the disclosure effect, displacement effect, and the closure effect. And also we look at the population size in the vicinity within 35 km of the closed power plants and operating power plants. So we generated this kind of table with 3 panels. The panel A shows about the closed effect with the estimated coefficient with the SO2 level in that specific region in the neighborhood. And we calculate about the population size, and we calculate the net closure exposure. And similarly, we calculate the net displacement exposure, use the estimate for displacement effect, use the SO2 levels, the absolute levels, and the population in that specific region. And we find that these two largely offset each other, and the net exposure, if we consider this number divided by the pure closure effect, it is only around 4.3% for the net exposure, for the net closure effect, which means that the previous paper may overestimate the effect of closed power plants if we do not take the displacement effect into consideration. Okay, so the next question is that if the displacement effect is so large, then what's the determinant of the displacement effect, and how can we mitigate the displacement effect? We have two hypotheses. One is that whether the cleaner technology can minimize the displacement effect. The second question is that is the displacement driven by within province trading limit? So what we're doing here is that we collect over 8,000 of the renewable energy plants in China, and then we calculate for the wind, hydro, solar, and gas power plants within 100 km of retired coal-fired power plants. So this data is also from the Global Energy Monitor website. What we're doing is that we look at the triple interaction between what we had before to identify the displacement effect, and with the number of renewable energy and a specific number of wind, hydro, solar, gas power plants in its neighborhood. And what we have observed here is that with increasing number of renewable energy, we find that the displacement effect is reduced, which in other words, that the cleaner alternative renewable energy can mitigate the displacement effect of coal-fired power plants. So to respond to the second hypothesis about the within province, cross-province import of electricity, the impediments, we generate this dummy variable, the number of import, which equal to 1 if plants located in province with electricity import from other provinces that exceed the national average, which means that they have more import from other provinces. So interact with this dummy variable, we find that with more imports from other provinces, the displacement effect is reduced, which again shows that one determinant is from the cross-province impediments. And if we reduce this impediments or increase the import from other provinces, we can somehow reduce or mitigate the displacement effect. Okay, So let me conclude, then we open the floor for the questions. So in this paper, we manually collect a large set of data on the coal-fired power plants and renewable power plants. Then we merge with a high-quality granular level satellite data on the pollution. We observe a reduction in the SO2 level in the surrounding area of closed power plants, which is around 2.4%. But we also observe an increase in the SO2 level around the opening power plants, which is about 1.7%. So if we take these two opposing strengths into consideration, we find that the net effect is only about 4.3%, which is much less than what we expected if we consider the population, if we consider the level of SO2 pollution in the local vicinity. And if we think about what is a reason for such kind of displacement effect, we think about two reasons. One is about this kind of renewable energy alternative, and the other is about the cross-boundary electricity dispatch. So if we want to reduce the displacement effect, we truly need to promote more of the allocation to the renewable energy sources, and also we need to encourage the cross-boundary electricity dispatch. So this is about the policy lesson we try to draw and try to promote. And for the following work, we want to extend a little bit beyond the 2014 one. We want to know what's truly happening after the 2014, when China really for this kind of market-based for the reforms, what's happening afterwards. And also we want to know more about the firm level behavior to make our story more fledged. Okay, so this is what we are doing now. Thanks a lot, and I'm ready for any questions.
Right.
Thank you.
Okay, thank you. Any question from the floor? You can actually unmute yourself, or if you have any other questions. Got one question from the result. Actually, do you see any correlation between the closure of this power plant and also the prices of coal?
We do not have the specific information for the price, which need to be vary across the time, right? But we do not have the information. But that's a good point. We are actually checking the price of them and also checking the price of the electricity, but currently we do not have the information.
Okay. Right. How about the displacement effect? Do you see any kind of constraint, in a border kind of effects? That means displacement effect may not go beyond the provincial border. Do you see that kind of effects, being contained within the provincial? Because I think, let's say, different province, what is the incentive for another province to sort of increase their pollution level just because, just to provide more electricity to the neighboring province and so on? That means the inter-province kind of trade-off.
The thing is that, for instance, if say Beijing and Hebei, if we import, if as a boundary, it should import from Hebei, which is closer, if at the boundary of Beijing. But actually what they're doing is that they would rather prefer some place within Beijing, but quite further away. Yeah, this is because it's kind of administrative boundary, which prevent them from the efficient allocation, also the importing. So actually we have done a kind of interaction of the within by province or by county or by city. So we find that this kind of obstacle is more happening by the province rather than by city or by county.
Okay. Well, any comments or questions from the floor? Right. If not, I think thank you very much, Fang Yi, for the presentation and interesting topic on the coal fire power plants and what is unintended consequence. Before we close to that sessions, maybe I'd like to make an announcement for next seminars, which will be 2 week time. The paper will be by Gregor Schubert from UCLA. His topic is the impact of cultural preferences on home ownership. Please keep an eye on the notice that will be sent up to you soon. And if without further questions, I'd like to close this session. I would like to thank participants and also Fang Yi for the presentation. And thank you very much.
Thank you. Thank you, Tian Fu. Thank you, everyone.
Thanks.
Thank you. Bye-bye.